This video, we're going to talk about dilutions. And I'm going to say that I think dilutions, this is the topic in chemistry that is the most applicable to your life. And here's why. Um, Being able to dilute something from a stronger stock concentration to a like less concentration is, I think, it's more part of our real lives. Like I can imagine if you get those like concentrated juice, like those juice concentrates in a freezer and you want to dilute it to make orange juice. Or if you get like concentrated like coffee, you can get like cold brew concentrate and you dilute it to make like the appropriate tasting coffee. Those are situations you might have experienced in your life. Just adding water to something to make it less concentrated. It's also something that comes up more in like jobs as well. I've got a friend who works at a machine shop. And so he like repairs machines and makes sure that the machines are all working like in a big industrial sort of situation. And part of his job and part of the job of other workers in the shop is adding coolants to machines. So the coolants come in smaller and very concentrated containers, and they have to dilute them to a certain concentration. They don't use molarity, they use other measures for concentration. It's usually parts per million or molality or something else. But either way, the same principle applies. They need to add water to these coolants. And each machine requires maybe a slightly different concentration of these coolants. And so they have to calculate how much of the coolant do you add and how much water do you add to the machine. And if they get the numbers wrong, it can really damage the machines and it will cause really big problems. And my friend, his name is Dallas, who was telling me about this, said that very few people in the machine shop really know how to do that. It's not actually very difficult. I'm going to teach you right now how to do it. But they don't know. And the fact that he knows and a few other people know make them really invaluable workers. It means that they're definitely going to be able to keep their jobs, just because if other people can't do it, then someone has to be able to. So it's a really something useful to know. I'll also tell you that there are like students when I was in college who still didn't really understand this concept. It's a little challenging, but it's actually not that bad. And I think you'll be able to get it without too much difficulty, and it'll be very useful in the long run. So let's talk about dilutions. Dilutions is when you add water. Anytime you add water or you mix two solutions, the concentration is going to change. It's going to be diluted. It's going to go from being very concentrated to more dilute. Adding water, but you're not actually changing the amount of solute. You're only changing the amount of solvent. So that's kind of what we're working with here. So there is a formula that can help you to do this, but you can also think of it conceptually. I'm going to kind of show you both ways. The formula is M1V1 equals M2V2. You need to know the molarity of the initial solution, the volume of the initial solution, the molarity of the final, and the volume of the final. But I want to walk you through this first example more conceptually, and I think it'll make sense. So we have 340 milliliters of a 0.5 molar sodium bromide solution. So that's what we have here. So this stuff is the sodium bromide. And we are going to add water to it. And we want to know what is the concentration after we've added this water. So here's what we know is going to happen. We know that when we mix these two solutions, I should have drawn this with the water levels changing, but you get the picture. If we add these two solutions together, we know that the final volume is going to change. We started off with 300 milliliters of the original sodium bromide solution. This is just water. There's no sodium bromide in it. So we're going to end up with, let's see, 340 plus 560. I think it's like 900. Yeah, we're going to end up with 900 milliliters total. So that is 0.9 liters. That's 0.56 liters. This is 0.34 liters. I'm just going to write those up there. Okay, so we're going to end up with almost a full liter, but not quite at the very end. But what we're going to notice is that the amount, the moles of sodium bromide don't change. They stay exactly the same because we haven't added any more. So this solution is more concentrated, and this one is more dilute. Same amount of moles, but in different volumes. So the way I like to think about this is the first question is how many moles of sodium bromide are in this solution? And then I'll know that that's how many moles are in the final solution, but the volume will have changed and that will affect the concentration. So let's do this first. Let's do this. Moles of NaBr in the initial solution. So let's solve for that first. So we have 0.34 liters in a 0.50 molar solution. That's moles per 1 liter. So 0.34 times 0.5 is equal to 0.71, 0.17, sorry. So that's how many moles. So that means that there were 0.17 moles in this original solution. Therefore, there also must be 0.17 moles in the final solution because we haven't added or removed any sodium bromide. However, we have changed the volume. So now we need to find final concentration. Separate calculation. We have the moles, we have the final volume. The final volume is when we added these two together. So that's going to be 0.17 moles in 0.9 liters. So really the math is pretty much the same as what we've been doing for this whole, the whole molarity section. So that's going to be 0.19 molar. That's our final answer. The original concentration was 0.5. We've now decreased it, which makes sense because we have more than doubled the volume. So we've probably at least halved the concentration. So these numbers make a lot of sense. So this means that this new solution's new concentration, this one was 0.5 molar. This one now is 0.19 molar, which is very different. Isn't that cool? Okay, so that's the concept behind this. So I did two separate calculations, and that's the way I like to think about this. I like to really think about the concept because then I don't actually have to memorize this formula. I can use the formula, but like to me, I'm just thinking about, oh, concentration is moles per liter. Here's what's actually happening. Let's keep track of all of the sodium bromide so we know how it's changing and how the concentration is changing. So that's one way to do these problems, is a little bit more conceptually. I can also show you how to do this using the formula. And in this case, you just need to know, let's see, I don't have a lot of space to put this. I wonder where I could write it. I can do it off to the side here, I suppose. So what we have is M1 V1 equals M2 V2. In this case, we have to know what we're solving for, which is going to be M2. We're solving for the final concentration. And we just need all the other numbers. So that is going to be, M2 is going to be equal to M1 V1 divided by V2. So we would need to know the initial concentration, which was 0.5 molar. The initial volume, which was the 0.34 liters. Sorry, I'm running out of space, but we're going to try our best. And then the final volume, so we still had to add the numbers together to get 0.9 liters. Okay, so you're going to see that what we end up doing to solve it this way is we end up multiplying 0.5 times 0.34 and dividing it by 0.9, which is the exact same math that we did here. 0.34 times 0.5 divided by 0.9. Same math, just a little bit different. So you can use either one of these methods. To use this one, you still have to understand what each of these means and be able to identify it correctly, or it won't work. So Let's give it another example, and then we'll go into the packet. And then we'll pick out a few more. Okay, so how much is going to be milliliters or liters? We're looking for volume here. Of a 15 molar stock solution, do you need to prepare 250 milliliters of a 2.35 molar hydrofluoric acid solution? So stock solution just means that it's like a really concentrated stock. I do not have this stuff in my stock room because hydrofluoric acid is extremely dangerous. It's not actually as acidic, or like, it's not like the pH is super low. What's scary about it is that the fluoride is attracted to the calcium in your bones. So it'll actually just like seep right through your skin, not really interact with the rest of your tissues, and just hang out in your bones and dissolve them over time. It's really bad. This stuff is dangerous. And 15 molar is insanely concentrated. I would never have this. But I do have to dilute other acids like hydrochloric acid. It's glacial, which means like 12 molar, which is very, very concentrated and very scary and dangerous. And I do like to dilute it down to something more like 2. So this is a calculation I have to do all the time. So in this case, we've got M1V1 equals M2V2. And we are going to be solving for how much do we need? I would call this one V1 or V2. You can kind of think of it either way. I think in this particular case, I'm going to call it, as long as we keep everything together, let's call it V1 this time, just for fun. So we want to know how much of this stock solution. So that's the stock, and the stock solution is going to come in some sort of like jar or bottle-y type thing. Here, I'll put a little handle on it so we know it's like a bottle. And this is going to be, it's got some water in it, and it's got a whole bunch of stuff. Very, 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 very concentrated. And it is 15 molar. And we are going to add some amount of it, probably another little bottle. Maybe this one doesn't have a lid. We want, in the end, 250 milliliters, which is also equal to 0.25 liters of a 2.35 molar solution. So that's what we're going from. So I'm going to call this situation 1 and this situation 2. So how much of this are we going to need to pour out and add to water in order to make this new solution? Okay, so that's what we're trying to solve for. So we're really looking for the volume of that. So that volume is going to be M2V2 over M1. And you can see, because I just did some little algebraic substitution. I skipped the algebra. Sorry. Hopefully that doesn't freak you out too much. Okay. Oops. Gotta get the lights back on. Okay. Just got a bit more time. All right. So M2 in this case is, we're going to call this our 2 or final situation. This is our initial. So the final, we want 2.35 molar, and we want 0.25 liters. So it's really important that whichever one you define as situation 1 or situation 2, you keep those together. If you kind of cross-contaminate those numbers, you're going to have the wrong answer. Our original concentration was 15 molar. That's the M1. Okay. So now all we got to do is solve. So 2.35 times 0.25 divided by 15 is going to be 0.039 liters, which if we want, we can also write as, let's see, 1, 2, 3. That's going to be 39 milliliters. Okay. So that basically means that in order to make the stock solution, we're going to need 39 milliliters of this. We're going to add it to 200. So 39 milliliters of 15 molar plus 250 minus 39, 211 of water. And that's going to equal 250 milliliters of a 2.35 molar stock solution. So that's kind of the way that we would actually make this. We might not go into that too much, but you do want to think about your final volume does need to be 250. So to actually make this, the fact that you're adding liquid, you can't add 39 milliliters to 250 because then you would end up with 289 milliliters, which would be more dilute. It would be probably like a 2.2 molar solution or something like that. And that would be wrong. So that's kind of the process there. All right. Dilutions are super cool. I would be shocked if we don't end up doing a lab related to this. Let's take a look at some sample problems. You have 2 pages in the packet. You've got page 11 and also page 12 that you can do this to practice this skill. This is a really big part of this unit for sure. So let's pick out a question or two. Let's see what we got. Let's see what we can do here. Maybe we'll do 3 and 4 just to shake things up a little bit. I think these other ones maybe you can handle. Let's do 3 and 4. I like them. So if I leave 750 milliliters of a 0.5 molar sodium chloride solution uncovered on a windowsill and 150 milliliters of the solvent evaporates, what will the new concentration of the sodium chloride be? So let's draw a little picture here. So we have a 0.5 molar solution, and it is at 750 milliliters, and we lose 150 milliliters. So what will the new concentration be? We also have a volume thing. So we've lost 150 milliliters. So we got to think, what is the new volume? That's important. Well, it's going to be a 750 minus 150, which is 600. So the new level is going to be 600 milliliters. But the salt didn't dissolve. So this is going to be more concentrated. So this is the initial scenario. This is the second scenario. So it looks like we are trying to solve for molarity there. So what we can do is we can use M1V1 equals M2V2. That would totally be fine. Maybe let's do the other method just for fun. Why not, right? So let's see moles. Let's solve for moles first. So to solve for moles, we've got 750 milliliters, which is 0.75 liters. Just dividing by 1,000. That's 0.5 moles per liter. So we can solve for moles. So that's going to be 0.5 times 0.75. So that's 0.375. So in this scenario here, there's 0.375 moles. Sorry, moles, not molarity, moles of sodium chloride. So there's also going to be 0.375 moles in the second scenario. So let's solve for new concentration, which is what we're actually solving for. So the new concentration is going to have to be that number of moles, but our new volume is 600 milliliters. Sorry about that. And by that I mean 0.6 liters. Convert that. 0.6. And so that's going to be 0.6, let's call it 6.3 molar. We'll round it. And that's our final answer. It is more concentrated, which is exactly what you'd expect. So there you go. Pretty cool, right? Okay. To what volume would I need to add water to the evaporated solution in problem 3 to get a solution with a concentration of 0.25? Okay, so the original was 0.5. Now we want it to be even less concentrated. We're gonna have to add a lot of water. So I expect that this final volume had better be more than 750. Actually, in fact, I think it's gonna be double that. So how to do this problem? Well, we can kind of pick whatever place we want to work on this one. But maybe we'll try M1V1 equals M2V2. Just to shake up our problem solving techniques. So the original, we are going to be solving for the V2. So V2 is going to be equal to M1 V1 over M2. So our original situation, we can kind of go with whichever one of these we want, but I guess let's go with this. We'll go with this kind of situation. This is our new M1. So our concentration is 0.63 molar. And the volume is, what do we say, 600, so 0.6 liters. And our new concentration that we're looking for is 0.25. And we want to see what the new volume would have to be in order for this to be true. You'll notice that the molarities cancel out, so that's cool. So let's take that and let's times it by 600. Oops. 0.625, oh gosh. And by that I mean 0.6. So that's that 0.375, which is good. And let's divide that by 0.25. That's going to be 1.5. So that's 1.5 liters, which, hey, is double 750 milliliters. What? I know, crazy. Okay, so our new, so we can just keep adding water and evaporating water, and as long as the salt will stay in solution, it doesn't get evaporated. So that's kind of part of the principle there. Okay, I'm going to leave you all with the other page, and we can always work on more of these problems in class together. But that should give you a pretty good head start on dilutions. Keep these pictures in mind. That's literally what goes on in my brain when I think about these. I don't really draw these pictures anymore because I have it in my head. But if you want to draw pictures, I recommend it. And we'll go over this more. It's a cool topic, and I hope that you will learn from it and be able to apply it in your everyday life. Thanks, y'all. Good luck.